Julian specializes in social engineering activities and network penetration. He comes from a business background and focuses on handling penetration tests with a business-oriented perspective. Julian is an offensive security certified professional and a Cisco certified network associate. And he's going to present the password Devourer. Take it away, Julian.
Thanks. See if this is working right. All right. Hey everyone, thanks for showing up. I know that pretty likely that a lot of you have a bit of a melted brain after the long day of talks. So I'm going to try to keep this as interesting and fun as possible. There's a good amount of statistics-based material in here, but we're going to try to lighten it up. So the talk is called Kraken Password Devourer. This is basically about punishing victims using statistics. So just kind of getting into the who am I here. That's me. If you have seen me before, you might not recognize me because my hair is now white, so that's an interesting feature that I've just started doing. So hopefully I'll keep this up and I won't be unrecognizable. So my name is Julian. A lot of people call me Hobo, so if you want to call me that, I will equally as responsive to that name. As he mentioned, I'm a security engineer at Praetorian. We're a penetration testing company out of Austin, Texas. We're sponsoring this room and your necks right now. So thanks for wearing those. But so I specialize in network penetration tests, and a lot of this is going to be focused on the type of engagement work that I do. And with the password statistics that I have, a lot of that comes from my penetration testing experience within a network penetration test for clients. And we're going to actually pull a lot of that type of information in here. So a little bit of background for this talk. My previous password cracking talks, I actually did this at B-Sides Austin. Some of you may or may not have been there for that. This is actually a follow-up to that. And some of the differences that I have for this talk, the last one was a little bit more focused around what are known as mask attacks, and I used statistics to show what the different types were and how you can improve upon that using efficiency and sorting it based on time. I'm going to show a little bit about that as well, but there's going to be more use for practical examples as well as some rule-based attacks and the full stack of a cracker's timeline and show you the different ways to make this very efficient. And one thing that I want to point out at this point, though, is that I'm not using some giant password cracking rig. That's not the point of this. The point of this is to show that this can be done efficiently and effectively using just your laptop. All of this statistics, all of these tests were done just using my laptop with a pretty semi-decent processor. It's not some giant monolith password cracking machine. So, but the implications, I think, for scaling that up, you could do that with, you could use the same methodologies and the same statistics to do this, and it would just scale much better. So, and I'll talk to that here in a little bit. I also want to point out that all this stuff is coming from a pen testing perspective. Now, the difference there is that when you're doing it at a pen testing perspective, I'm only caring about initial compromise. I only want administrative credentials. I don't really care about your individual password necessarily unless you happen to have some sort of elevated access. So just keep in mind that when I'm talking about these things, I'm not looking to get necessarily 100% compromise on these passwords. I just want the initial compromise, and then I can move around from there. And I'll show you why that only matters in this situation, and I will still get your password anyway. So why is this important? So if we actually talk about, most of you are probably here, you're blue teamers, you're defensive, you're working for a company, and you're trying to secure your own crown jewels. Let's think about LinkedIn, eHarmony, and Rocky. You might be familiar with these, especially the newest Ashley Madison stuff that came out recently. All of these companies were breached and then eventually had a password dump happen to them. And this is interesting because in each case, they've done something that has caused them to be able to be breached and the password dump to be more vulnerable than it should be. And we'll go into a little bit of that in a bit. But I don't want you blue teamers to tune me out and just think that, well, this is only a red team exercise. This only matters for if you're trying to crack passwords. That's not true. This matters for protecting your own environment and protecting your crown jewels and things that you can do to stop it, from my perspective, though. And then the red team, we're going to show them, why not to do these things and punish them for doing so. So Ashley Madison, what did they do wrong? I'm sure that if you're sitting in this room, you've almost definitely heard about the Ashley Madison password dump and the breach. But what did they do wrong that recently came out that caused the passwords to be able to be more vulnerable than they should be? And this is a case of bad implementation of security. They had a bcrypt, which if you came to my talk last time, I actually vouched quite a bit for bcrypt as a mechanism to hash your passwords and be able to do it more securely, because bcrypt takes a lot longer to generate the hash for than, say, MD5. Now, what the Ashley Madison folks did here that messed them up is they had a field called the login key. And this login key was when it was originally looked at the code, it was a bcrypted concatenation of a lowercase username : password, right? And that inherently isn't so bad. In fact, that was MD5 hashed at the end as well. And that's not so bad, except for a team called Cynosure Prime figured out that it hadn't always been this way. So let's say that maybe their CISO came to them one day and said, "Hey, our hashes are all in MD5. We should try to use bcrypt." Okay, sure. So they bcrypt all the login keys, or maybe perhaps the session variable. And they said, "Okay, well, it's done." Well, that's fantastic that they changed the code to do that, but that didn't change it in the database. So all of the what Cynosure Prime found out is that previously it had just been that they used the MD5 hash of those things, which is quite easily calculatable as opposed to bcrypt. And so by doing that, they didn't actually change all the ones that had been done previously last time. So all the ones that were MD5 in the database already stayed that way. And they could have refactored it to make it better and more secure, but that would take time, and who wants to do all that? So they just decided not to, and they paid the price by having a lot of compromised accounts after that. So we're going to go through some of the different attack types for password cracking, and I'm going to kind of walk you through this, a little bit of a different sort of graphic here, but it's what I would call the cracker's timeline. And effectively, what you have here is the 5 major different attack type vectors for password cracking. On the one far side with a bunch of key space, you have brute forcing. You can go through a ton of key space, but it will take you, almost an infinite amount of time to get this done. And on the far other side, if you have a dictionary or maybe a password dump, you're just going through iteratively to see if people are using that password. And then you've got different ones in the middle. And I'll explain a couple of different steps and how each different part of a penetration test can showcase where these come into play. So, but potentially, let's say all of them are useful. Brute force is not useful, because you can have a maybe 7-character requirement for your passwords, and since 7 is so short, it's much more easy to brute force all 7-character passwords than necessarily just guess them for a while out of a word list. So it definitely, you want to tailor your targets to that, and I'll describe this more coming up. So here are some of the different techniques explained a little better. Like I said, dictionary attack, you just have a list maybe of password dumps, or it could even be English words, and you're just kind of iteratively going through and seeing, does this password match? Rules-based attack is my personal favorite. It's a really nice middle ground, and this is what this talk is going to be a little bit more focused around. But it is interesting because it's really how people come up with their passwords. You come up with some word or something that matters to you, and you add some symbols or some numbers onto it, etc. And then the mass structure attack, which is what I spoke about at my last talk, we'll go into a little bit. But it's kind of analyzing the structure of how people use their passwords. It's not necessarily like augmenting as it would be with a rule set, but rather it's attacking your actual structure of it. And what do I mean by that? So the structure of your password, let's say in this example, for instance, your password starts with an uppercase alpha character, and then it is preceded by a whole bunch of lowercase alpha characters. likely being some type of word with a capital beginning. And then the interesting part about that, though, is that with a mask attack, you can just specify each character, and then it will iteratively go through every single possibility that matches this mask, and then it will see if all of those match. So these 3 examples on the right are some things that would match those this mask structure that you see here. So that's interesting. When I first learned about that, I thought this was pretty cool, so I tried to do a little bit of research on that. So here's where some of the statistics come into play. So my question, by analyzing all of these different password dumps that have happened in the past, do universal password structures exist? And if they do, what does that mean, first of all? When you're creating a password, my theory maybe is that it's likely people have a tendency to make structures similarly within their passwords. It's probably not just some random conglomeration of it's a symbol and then it's a letter and then it's another symbol. There's probably some kind of actual pattern to it, right? So what would it look like if we map this out? If we were trying to see, do these actually have the same structure? So I analyzed all of these and I associated a masked structure to it, and then I graphed it by popularity. And this is the result that you see. And so this is actually a pretty incredible slide. If you take this in for a bit, I'll kind of explain. But this means that at the very beginning, the first 13 mask structures comprises 50% of the entire amount of mask structures that existed within what I analyzed. And there were around 260,000 of these mask structures. But 50% of all of those passwords were within this first 13 sets. So that's pretty incredible if you actually think about it. That means that there's very little variance in what people are doing, which is not surprising. People like patterns, and it's easy to come up with that type of stuff. So let's simplify this a little bit and understand it. If I see consecutive letters within a mask structure, let's say if I'm looking at a particular structure, it's uppercase letter followed by L, 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 indicating a whole bunch of lowercase letters, we're going to assume that this is a word for good reasons. It's very much more likely that people have a password of potatoes than pivwizjig, because that doesn't mean anything to us. Potatoes means something. We understand that that is a pattern in itself. That word means something to our English mind, and then we interpret that as something. So this is actually a form of hybrid attack, which was on that graph that I showed you, where you're in fact converting all of these consecutive letters into a word. And you can leverage a different type of attack against that called a hybrid attack, and it covers more key space, but it's a little bit more focused. It's a little bit more focused than say your mask attack, because you're just guessing maybe they're using a word here as opposed to just let's try everything that they could possibly have there. And I want to test and show you some of these mask structure attacks that I did on a actual set of hashes that I compromised for an engagement. So there's a lot of information on this slide. Kind of go through it briefly, but so we have the top 10 mask structures. What I did is I took the top 10 mask structures that existed for something that required an uppercase character and a digit. So when that happens, I took those top 10 and then I sorted them by the amount of time I knew it would take to crack them. And the time is arbitrary in the sense that I did it on my laptop, so the minutes don't mean exactly, but if you can scale it, this was actually done quite slowly. If this was done on some giant server with tons of different GPUs, then you could do quite a bit more damage to these hashes. So what I wanted to do is I wanted to bar my time at 1 hour. I only wanted to crack hashes for 1 hour and then be done with it. So in this particular case, the shortest amount of time, digits, the one with 4 digits at the end, because digits are easier to crack than letters because there's less of them. So what I did is after 1 hour, I ended up being able to compromise 491 accounts, and that's 11% compromise of the entire hash set. So the question though is, does this align with the statistics that I showed on that chart. And it is a little bit less because you would think that the top 5, which is what I was able to get to, would have more than 11% of the passwords in there. And that's true when you take into consider, though, that a lot of the hashes that you get from like a domain hash dump, a lot of them are going to be machine accounts. And so that's going to skew your results just a little bit because those machine accounts are randomly generated and not actual users who are coming up with passwords. And then you actually do get more passwords, though, from bad system administrators who like to make the same password for all of their service accounts. And we'll talk about that more in a bit. But 11% compromise for 1 hour of arbitrary cracking against a hash set for a targeted brute force attack is pretty good. And again, all that I care about for this is that I have some form of initial compromise. If I have one type of every user, that's also good. Like I want someone from HR, I want someone from the IT sector, etc. So here's some interesting statistics for patterns that I like. 90%, more than 90% of passwords require a capital letter. If you have a password that requires a capital letter, it's probably at the beginning, right? If you even think about your own password, I would imagine that a majority of you in the room, if your password has a capital letter in it, it's probably at the beginning. And that's an interesting fact. Just it works out with the patterns that we like and that we associate with it. It's just how we do words and sentences, so it makes sense to us, so we put it in our passwords as well. Here's another interesting, funny pattern that I like. I like to think that there's a magic sequence here. 2143. What does that mean? So if you're requiring a digit in your password, it's most likely going to have 2 digits appended to the end of your password. And that's kind of different because, why 2? What are the points of doing that? Why don't we put it in the middle of the password? Why don't we put it at the beginning? It's just what people do. People tend to put these at the beginning of the password or at the end of the password based on these statistics. So let's look at a specific one from the LinkedIn dump. So if we have the LinkedIn password dump, the top 4 mask structures requiring an uppercase character and a digit is this some uppercase character followed by what is presumed to be a word, and then 2 digits. And that matched 219,000 different passwords, which is pretty incredible. If we look at PHP BB dump, you see the exact same trend in the exact same place. 2 digits followed by 1 digit, followed by 4 digits, followed by 3. And that's kind of crazy to think that just even across 2 websites that this same statistic shows up. And then you continue. You even look at the biggest clear text password breach that has happened, RockU. You see the exact same pattern all the way down the list. So that's pretty incredible. Maybe there is a magic sequence, 2143. You have an extremely good chance that if it is requiring a digit, that's what it's going to look like. And if we look at the percent of total of all the things that makes up, these top 4 represent 35.5% of all of the passwords in there. So that's pretty incredible just to think about it that way. Another funny pattern. People tend to like to change alpha characters for symbols when it is required of them. So when I was doing my analysis and looking at symbols, an interesting pattern showed up that I didn't necessarily expect. Right off the bat, I thought, well, people are just going to append the symbol more often than not. But this was the top representation from the RockU password dump. And it has the symbol in the middle of what appear to be 2 words. But really, what's happening is that they're doing this, where you have one S turned into a $sign, and the other 2 just presumed to look like words based on the structure that was set up. So that's pretty curious. And then what we're going to do, though, is based on all this stuff that I'm showing you, it's not arbitrary, we're going to end up putting it into something that helps us crack passwords even better. And what I like to call rule-based attacks, I think it's the best because it's the best middle ground of hash cracking. You get to take all of those ideas and those thoughts, and you put them, those statistics, and you put them into augmenting password lists. And I'll show you how that works. It uses you can use, Hashcat, John, any different type of password cracking suite, and they have their own sort of custom grammar let's say, for the way that you come up with these rules. But they're all quite the same, and it's really things like, let's append one exclamation mark to the end of the password, or let's just capitalize the beginning of it, etc. And what's interesting about this is that for rule-based attacks, generally when people are doing red team assessments, or at least from what I've seen, people like to use what is called the best 64 rule list. And this is what was the result of a competition that happened against the PHP password dump in 2009. And so the competition was whoever can crack the most passwords with 64 rules will just make that the best 64 rule set. And that's what happened. But this is coming off on one website in 2009, and people are still using it today, and it doesn't necessarily make sense for what we need to do. So I set out to make improvements on this because I felt that it was severely lacking. So let's actually look at some of the things from the best 64 rule list. So it's a standard, but I don't get it because it was done way back in the day. Well, I mean, 2009 is not that long ago, but since security evolves every day, it kind of a while ago, right? So there's a lot of useless rules in there, and don't bother trying to read all that really quick because I'm going to take you through a nice little fun step-by-step demo of this. So this is, again, a rules-based attack is something that we want to see augment the password in a way that users would create it. So if you have a password, let's say your password's password in this case, and you want to make it secure, what you're going to probably do is put some symbols in there, you put some numbers in there, and so these rules attacks are supposed to emulate that. But some of the rules that came up in this best 64 rules list are a little weird. So let's say you have your password. The syntax that you see above it, the +5, bracket, 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 all that is the syntax for the rule that is what is described below. So let's take the 5th character of password and increment it by 1 ASCII value. Okay, sure. And then let's delete the last character, okay? And then move the last character to the first position 4 times. All right, and then we do this. I'm not sure why you would do this to make your password, but all right, sure. And then we're going to cut off the word at the 5th character. Okay, 5-character password. Someone's probably not doing that anymore. I don't think that's even allowed nearly anywhere by standard defaults unless you've explicitly requested 5-character passwords. So that's what we get as a result of augmenting the word password. That makes no sense. There's probably never someone who took the word password and did these things to them and then came up with this result. Now, I'm not saying that this never hits, because you could end up coming up with something that just happens to go through this process and makes a different thing that became someone's password. But my theory is that that's not very likely, and the whole point of this is to get quick compromise and do the best and most efficient rules that is possible. So I want to do one more example of it. It's not just a one-off. There's a lot of really strange rules that don't make a lot of sense in this. So let's take the password HouSecCon, which really by itself is a pretty solid password. It's got symbols in there. It's kind of weird and messed up. But if we assume that someone is attacking the HouSecCon web page or something, we're going to assume that let's put HouSecCon in that word list because that's probably or maybe what their password is based on, or at least it's a good guess, right? So we're going to swap the 1st character with the 6th character. Okay? Sure. And then delete the 4th character, so there goes the period. Duplicate the remaining combination. Yeah, it's actually, this is a pretty good password. I'm not sure why someone would do this, but I can see that that's a pretty good password. But then we truncate the combination at 4 characters. Why? That doesn't make a lot of sense. And then we duplicate the remaining combination. No one is doing this to their password. And if you are doing this to the password, then you went through a rule list that is meant to crack your password and use that to generate your own password, which is actually insane. So really flawless work there with that rule set. So a little bit about the set that I came up with. Again, I created it for the quickest initial compromise, and I optimized it for engagement work. right? So when I go in and do a penetration test and have to crack hashes, my goal is to get them as quickly as possible, and I use each individual compromise when I get more hashes as an opportunity to improve my own rule set. So things like appending the current year. In 2009, they did not append 2015 very often. But they do now. People love using the password spring 15, summer 15, your company 2015, etc., because we're on 90-day rotations, and people just say what's on their mind for that. And I also utilize the statistics that I showed you in the previous one. Capitalize the first letter. Do things like appending 2 numbers at the beginning or at the end. 23, for instance, is an extremely popular number to append at the end of your password. I don't know why, but that's what people do. So let me actually show you firsthand that on different engagements, this is better. So I did a separate engagement where I tested the best 64 rule list against my own. RockU by itself, the password dump that came out, so a dictionary-based attack, cracked 914 passwords. And that's not bad, really. 914 is still pretty good compromise, but let's say we wanted more for whatever reason. We didn't compromise the right accounts. We want a system administrator account, and we didn't get one on the first try. So best 64, you get 9,161. That's not bad. That's pretty good. But I think 12,749 definitely beats that, and that's because it is more modern and it uses different statistics that I leveraged in that approach. And so that's a 40% improvement over what a lot of people use as what I would say is the industry standard for using that rule list. And there's a lot of better things out there, but people just tend to use the default because it's what they know. So what I want to do now is kind of go through a full sort of attack scenario here. And we'll do this kind of quickly because I'm a little behind, I think. So we're attacking the Acme website. So first, we're starting off at a brand new penetration test against a website. We use Burp and different our browser to kind of spider the application and see what we can find here. And then let's say we come across a I forgot my password section. And this is interesting because oftentimes out of this comes a user enumeration vulnerability. And that can be in different ways. Perhaps the app, when it returns to a text message, it says, oh, well, your password's incorrect. Well, that means that their username isn't incorrect. So now I know what one of possible usernames are. And then you can also do this based on the time it takes for the server to respond to you. If it takes longer, then potentially it's a username that is valid, as opposed to invalid might take a shorter amount of time, etc. So let's say that we end up finding HTTP basic auth, which looks like this in case you're unaware. But when seeing this, now we know, okay, we have a potential thing to guess passwords until we get something right. And it's a very good target, really, to just try to brute force, or not necessarily brute force, but targeted guess, because there's an infinite amount of tries, there's no lockout attempts, and it goes instantly. So now that we've seen that, we're going to make a dictionary based on it. So we gather our dictionary based on dumps. There's a cool tool out there called Cool, which scrapes websites for unique words, and it packages it up, and you can append that to a dictionary as well, because a lot of people tend to use either usernames or passwords based on their company. And then we run that through a rule set like the one I mentioned before, that will help augment those to come up with a more targeted password. So people like to use the password. It happens in every single engagement that I run. But sometimes it has dollar signs as S's. So you just augment in every which way, and then that is your attackable word list. One thing though that's important here, people, even when they do this type of augmenting against a web application, you don't want a ton of data, and you especially don't want a ton of data that's not even going to work. So what you need to do is prune it. And what I mean by that is, let's say you have the password, but you didn't put any symbols, you didn't put any uppercase or anything like that. And you know what the requirements of the application are, and you know it's not going to fit that because it requires a symbol, it requires a digit. So you're going to have to, you don't want to test that password because that's just wasted time. And a lot of people will do it anyway just for the fact of using some default methodology that doesn't require pruning those out. So if you strip out all those impossible passwords, which is really important, I'll show you in a second, it's a huge decrease in the amount of things that you're sending and calling to this attack. So if you're throwing all of these usernames at usernames and password combinations at it, you don't really want to do several million attempts. Someone's going to shut you down eventually, most likely. So you want to make it as small as possible so that you can get in there quicker. So let's say that it required 8 to 10 characters, and let's say that an example word list that I put together that I like to use has 4,000 words in it. If I augment it with my 64 rules, it has 263,000 possibilities in it, and that's a lot. But if we prune that down to the amount of things that meet the application's requirements, then we get to like 12,739. And that's a huge decrease. That's 4.8% of that total. And that means that largely, over 90% of it is not going to ever work anyway. So why are you testing it against this application? So would I want to use 12,000 passwords against an application? No, that's too many. But let's say that we had several different words, just the words password and the website's name, etc. That might be a better target for this. The reason I use so many, though, is to illustrate the decrease in percentage. So if the tool that I'm kind of slewn together with different things, this is actually the syntax that I use to help prune that in this example. So let's actually run the attack real quick. So we use Hydra to guess the username and the password. Unfortunately, let's say that in this case, we ran into the fact that it was the username and password were the same, which isn't unfortunate. It's just kind of annoying because we did all that work before to get it all ready, and it just ended up being really admin or something. But it's not surprising. Like Ashley Madison had 630,000 accounts that were like this, and that's pretty incredible. And it's not unlike other things that I see within an organization. And then let's say that whenever we're on the authenticated side of this application that there is some SQL injection point that we have. And then we can use either our own crafted command or a SQL map to get Active Directory credentials via the backend MS SQL command prompt. And so with these hashes now, it's another step that we got to crack hashes. So we guessed a password using either a dictionary attack or a rules-based attack. And now we've got Active Directory credentials that we can crack any number of ways. This one's pretty important because this is our foothold in. So if we crack that SA account or we crack whoever domain account is in there, then we can move further into the environment. And that might require some sort of mask attack where we're really trying a lot of different vectors against it. But more than likely, we can get one of them with a rules-based attack and do it quicker. So, and then we have lateral movement. After we've compromised that hash, we can move around within the environment until we find a domain administrator, which is really our target. The domain administrator has all the keys to the kingdom, and we want everything that they have. So if we move around laterally, we can find that domain administrator and crack their hash as well, using the same idea. And then finally do a full dump from the domain controller on the environment of all passwords that are in that domain. And often you can get a lot of passwords from that. Most of the engagements I run, it's often like 60,000 or so passwords from the domain, and that type of compromise is what is really scary to people. And being able to crack the hashes in every step of the way is what matters to be able to do this. And like I said, blue team guys, there's possibility every step of the way here for you guys to stop this. Hardening credentials on each individual step here. So it's interesting though because I never seem to run into issues where that's the case. So just making sure that all of the stuff that you guys are doing when you're protecting your own keys to the kingdom, that every step of the way is going to be difficult for the attacker. So just a couple more things though, wrapping up on some other thoughts. Password reuse and default passwords. Reusing passwords is bad, okay? So password reuse, it's a huge problem. And it's not just a problem with users, it's a problem with the administrators who are running the network as well. 6,644 of about 20,000 accounts with reused passwords on a particular example from a recent engagement. That's a huge number. That is 33% of all the accounts in that environment. So what's happening here is likely, and more often than not, people who are setting a default account for all of their users, and then users who then do not ever change them, and then also system administrators who are deploying service accounts, all with the same password. These are both very, very bad practices. Or let's say, for instance, a little bit different, that you have cracked some strange password, and then another strange password, but they seem to be in the same form. So then often when I see that type of thing, which I do, I feel like, well, maybe they're just generating some default type of password. And that's often the case. And so what I'll do is I'll just run a hybrid-based attack using that word as the prefix and then the exclamation mark, and then just every single number within 3 digits. And then I'll compromise a lot more accounts that way because it's just being randomly generated from that system administrator. And then the reason I don't care that I crack your password specifically because your password's really, really hard or it's really long and no one's ever going to guess it, it doesn't matter because there's the sometimes you just get screwed anyways case. And this is called Mimikatz. Mimikatz or Kiwi can pull your clear text credentials from memory if you have system privileges. And this is still not necessarily being mitigated fully. It's just based on the way that Windows works, but there is some interesting stuff in the works that allows Mimikatz to have a honeypot of sorts that has a whole bunch of fake credentials in it, which could slow down the attacker. But other than that, there's really not anything that even I've run into at all that helps stop people from pulling clear text passwords from memory. So if I compromise the person who's using password 1 from their account, I'll probably just move laterally and then find your password sitting on the workstation that I have system access to. So one thing that I am also incorporating into the kind of slewn together tool that I'm talking about is this. It's in the pre-alpha planning stage for this part, but it's refined rules via machine learning. And I think that this is a really interesting idea because what can happen here is that what I'm doing currently is a manual process of just trying to see, okay, how can I improve it based on my next engagement? Are there things that I'm missing after cracking a whole bunch of them? But if you actually do a sort of a machine learning style thing, you could sort the passwords based on how effective they were against a particular dump. And then it can evolve over time. You can have any number of rules in it, and just as a pen tester or as a blue teamer doing a security audit of your passwords, you can say, okay, well, I want the top 100 rules because that's what I have time to look at. And then running those 100 rules against that, you can see how much is compromised from there. And it's the same concept that I was talking about and did with the mass structures as well, doing all of the top mass structures and listing them based on efficiency. This is the exact same idea, but using machine learning. And I think that it is a interesting and bit of a cool project to start working on it for that. But that is still kind of in the works for this. So a couple of takeaways from ideas here. Implement security, don't just buy it. That doesn't mean that you have to have purchased something. Don't, apply bcrypt to your code and then realize that all of your passwords are still an MD5 in your database. It didn't matter that you applied that first part if that second statement is true. So be a password rebel. You don't have to put an uppercase character at the beginning of your password. You don't. You don't have to put 2 letters or 2 numbers at the end of it. And just just come up with better ways to do it with your password. Mix it up, throw some other stuff in there, use some mnemonics. Don't use correct horse battery staple from the XKCD comic. And then don't use the best 64. Don't try to use all these defaults. Using defaults often leads to security risk in every case. So there's a lot of things out there. Like I have my tools and my stuff here. There's stuff online. Minga from CoreLogic has some good password rules and whatnot that exist online as well. And then two-factor authorization. It fixes so many things. There's no reason not in many cases to have that applied throughout your environment. Obviously there's some things that it doesn't apply to, but in cases where it does, make sure it works and make sure it's secured. So last thing, for all of this password stuff, all the tools and the rule sets and the implementations that I've done for these things and statistics, I'm kind of going to, in a way, I want to show you guys that and leave it open for you. But I'm going to kind of make you do the work and contact me if you want to see it. If you would like to work with me on either improving it or if you'd just like to see what I have currently, feel free to either reach out to me and tell me that you're interested or that you just want it for your own password audit, etc. But that's all I have about that. And thank you very much for listening. And then definitely, if you have any questions, now would be the time to ask them. Anyone? Anyone? Yeah, I like that idea as far as that would be a cool thing to use for a password generation idea, but in actuality the Best64 competition was based on the PHP BB dump. And what likely, yeah? Yeah. Well, that would be interesting because that would be a pretty bad password generator in my opinion, but yeah. Yeah, sure. I think that any type of generating passwords based on really static thoughts like that would be pretty silly. But yeah, awesome. Yes. Yes, absolutely. The length of the password, as you saw with the the mask type attacks, definitely matters because if you have a really long length, you're not going to get it with that 8-character mask structure that I had. And in general, length is the best thing that you can do for a single-factor password because of the different key spaces that it would take up. That being said, though, when people make really, really long passwords, it's interesting because if your password is, let's say, 30 characters, but it's not randomly generated, then you probably put some pretty severe structure to it. It's probably some sort of mnemonic that it could be that you mixed in symbols and characters and whatnot, but if it's that long, and there's a good chance that it has a lot of structure to it that could then be guessed. But it is still more secure than having a shorter password, yes. I always recommend to my clients to do 10, and I think that that's kind of on the border of still insecure in my mind, but people really push back after you say any much further than that. So I would generally say 10 is what you should strive for. 7 is unacceptable. 8 is unacceptable. It needs to be longer than that. Yes. Yes. Yes, exactly. And to your point there, LM hashes, which is sort of a bit what you're talking about, after it reaches that 14-character mark, you can't actually have that password anymore because of the very insecure LM hash implementation does 2 sections of 7-character passwords, and you can crack them individually. So that if that's the case, since that's the case, though, you really shouldn't ever be using LM hashes in general due to that security flaw. And that only really ever happens with legacy systems. So if you have Windows 2000 in your environment, XP in your environment, which I still see every engagement, you need to move off of that so that you don't have to use those LM hashes anymore as well. Right, exactly. Yes? Yeah, and that's the interesting part. If your password has some different language characters in them, then I'm probably not going to crack them. But again, I want to point out that I'm not necessarily interested in your password then. What I'll probably do is find someone else's password and then laterally transition to your box and then dump clear text credentials from that and go, oh, interesting. You have a really strange password that I wouldn't have cracked unless I did this. So. Yeah, exactly. Yeah, two-factor authentication and things like LastPass help really manage your ability to do passwords effectively. And I know that some people think LastPass and things like that are a security risk because it's all your eggs in one basket. But then I would challenge that with the fact, okay, you can memorize one really secure password. I believe in you that much to memorize at least one really secure password that you can use. And then if you have two-factor authentication on top of that, then that does a very good job at securing you. And if someone compromises you from there, then you really have someone who wants what you have, or you were going to get caught anyway. Any other questions? All right, thank